Welcome everyone to my class or to C-based VLSI design. In today's lecture, we are going to discuss the resource allocation and binding problem for hierarchical sequential graph. So, we have understood that this allocation and binding problem is something where we map these operations of the behavior into function units and the variables of the behavior to the storage, specifically registers, RAM, ROM and memories. Okay. So, and we have seen that these particular problems we have to take these two problems separately, this operation to function unit binding first and then variable to storage unit then, right. So, we are discussing the first problem, that FU allocation and binding, and then what we have seen that in previous classes that we can map this particular problem to either graph coloring problem or clique partitioning problem, right. So, that we have already discussed, and then also we have understood that this particular problem is actually NP complete problem. That means, it is a computationally hard problem. That means, we do not have any polynomial time algorithm to solve this problem efficiently, right. So, then we have seen that this particular problem is for a particular class of problem where this particular complete graph is an interval graph. We can solve this problem efficiently. What does it mean? We can actually have an polynomial time algorithm to solve the problem, and then we have seen that we have an left edge algorithm which can solve this problem easily. And also we have discussed that if we try to solve the problem of FU allocation and binding only for a particular basic block, right, then this particular problem is actually can be solved in polynomial time, right. That part we have already discussed. So, in today's class what we are going to discuss is that, but in general when you given a program, it is not only consist of a single basic block, right. It consists of set of basic blocks and which is basically have a control dependency, which is basically have if else, we have loops and also function calls, right. Function call is very common in C programs, right. So, in this particular class we try to understand what will happen if we try to solve the problem of this allocation binding corresponding to the whole graph, right, to the complete hierarchical graph. Right. So, that is something we try to discuss today, and we will see in under which circumstances this particular problem will be will fall into polynomial time algorithm, and under which category it will not fall under this polynomial time algorithm, and we have to solve it is a heuristic algorithm, because that problem will remain NP complete. Okay. So, that was the things we are going to discuss today. So, first we will understand what is the hierarchical graph. So, hierarchical graph is something is where you have say basically in C program what you have write. So, you write a sequence line of code and then say you have a function call here, right, you can have a function call here. So, you have some code here, you have a function call here, then you might have a branch, then you do certain things here, you do some certain things here, then you come back, you do something here, and then say suppose you have another condition and then you do say some set of operations in loop. So, this is loop, and then once the loop ends you do something, right. So, this is basically function call. So, function call is nothing but another body, and then this is if else, right, this is function call and this is loop, right. So, this actually this control flow actually is the realistic one, right. So, we have discussed that if we have a straight line of code, there is no control flow, there is no if else, there is no function call, there is no loops, there is a straight line of codes, that means a series of codes written there. If you take that only one basic block, that is then we can actually solve this allocation binding problem efficiently using left tail algorithm, because the complete graph will become interval graph. But in general, when you consider the complete graph like this, which is the realistically your C code will be like that only, then how your this complete graph looks like, and whether that particular remain is the complete graph will remain a interval graph or not, that is something we need to understand. Okay. So, let us understand the hierarchical sequence of graph first, right. So, suppose you have a straight line of there is a code like this and there is a function call here, right. If I try to map this particular diagram to a realistic code, it is like this, right. So, suppose you have A equal to B star C, and then suppose D equal to A star F, right. So, this is that part. So, this is I am mapping to this is my A and this is my D, and say this is say x equal to y plus z, this is that operation, and then you have a function call, right. So, suppose we have a function where I am passing x, y, say x, y and z, and I am getting the value into say in m, some variable, right. And in the function what I am doing, this is this body, this is my main function. So, this is my say main, right. So, this is my main. So, I can delete this part, right. So, this is my main function, and then I have say this function body, say this is the function where I am parsing x, y and z, and what I am doing here, say x plus, say suppose I am doing say x say a equal to x star y, and then some c equal to y star z, and then say there is a plus operation here, and then there is a NOP. Okay. So, then say I am sending this out equal to a plus c, right. So, suppose this is what I am doing. So, now you have this code. So, this is a straight line of code, there is no only here there is a function call, and then in the function call we have this body where I am just doing these two operations. This operation is this operation is this is plus, and then finally, I am sending this out as a return, right. So, this is I am returning. So, now this is what the hierarchical graph looks like. Right. So, now I have scheduled this particular main block, because this is a basic block. I also schedule this basic block, right. I have a schedule, and now I have to schedule together. I have to merge this club, I have to club these two schedule together, and I will get a combined schedule graph, right, combined sequence graph. And then on top of that, I am going to do the resource allocation and binding, right. This is what is about the function call. So, now you have if else is also similar, that you have a say main function, and then suppose there is a if else call here, right. So, if I just try to map this into a realistic code, it like this, it is similar to the previous code that I have say a equal to b star c, this is this operation, then say this is d equal to a star e, right. So, this is this operation, and then say x equal to y plus z, this is this operation, and then suppose I have a function call, right. So, suppose some condition, under certain condition, if this condition is true, then I am going to do say p equal to x plus y, and then and say q equal to x minus y, right. This is the operation I am mapping these two operation. These two are basically independent operation, and then else there is nothing, right. So, else nothing is there, right, nothing. So, then what will happen, this is my if else if branch. If branch is also a basic block, and which is this code, and else branch is there is nothing. So, this is NOP, NOP is the no operation, right. So, and now if you have, this is the main function, and this is my if else, and then this is my combined sequence graph, right. So, I will schedule this part of the basic block once, I will schedule this part of the basic block once, I will schedule this, there is no operation, but it might operation might happen there, right. So, now you have the combined schedule graph, right. So, I know the what this is the overall combined schedule graph, and I want to do the resource allocation and binding problem for this particular graph. Okay. So, this is what is the if else thing. Okay. And then the same next part is the loop, right. So, this is the loop, and loop is something you have a loop call here, and then this is the loop body, and you know the loop body is something, there is a straight line of code, right. So, you can suppose, so basically you have say some codes like this, say you are doing something a equal to b plus c, then I equal to 0, and then in the for loop I equal to 0 to 10, you are doing say a I equal to b I plus c I, right. So, then what will happen, this is in the this is the, so in this part this code is basically mapping to the sum of the nodes here, and then you have a loop body, and the loop body is this. So, you have another sequence graph here, say it will be like this, say you are doing like this some plus operations, you are having a operation where you send a, send I, it will give you a I, you have another node where you give b, you give I, you will get b I, and then you will get the result x, and then you basically have another node where you give I, you give c, you give x, then it is basically here it is happening equal operations where basically c I equal to x, right. So, this is how you can actually this is read operation, right. This is read and this is write, and this is a plus operation. Okay. So, this is how you can actually draw this sequence graph for this loop body, and then you basically schedule this loop body independently. You independently schedule these operations, you independently schedule this the main block, and then you have a combined sequence graph, and you try to do the resource allocation and binding problem for that combined graph, right. So, we understood that even along with basic block, the main control flow in the hierarchical graph is function call, which is primary, and then if we have if else, which is branch, and we have loop body, right. So, that if else I try to mean that it is a conditional branch, it can be switch case as well, right. So, I am just try to give the branching thing, and the loop is can be while loop, do while loop, for loop, anything, but I am just try to say the loop. Okay. So, in general terms. So, now what we are going to discuss here is if you have function calls, how your conflict graph look likes, whether this particular problem will remain interval graph or not, that is something I am going to discuss now. Okay. So, first of all, you try to understand one thing. So, we have function calls, right. When we write function in a program, so suppose we have a main and you write, so you have some code, then you say call the function, right, and then you again after some time you call the function. So, when we write certain things in a function, when basically that particular code is going to repeat many times, right, instead of repeating the whole code in the main, I just write a main one copy of the function, right, set of lines, and then I am going to call this function many times, right. So, that my code size remain small, right. So, what does it mean? We have a repetitive kind of operations which has to be executed multiple times, and then what we do, we basically take that particular repetitive part of the code into a function, and I am going to call this particular function multiple times, right. So, that is the purpose of function call in C program. Okay. Now, you think about you have a one copy of the function. Now, you think about I am a hardware, right. So, in the hardware, what usually happen that this whole operation going to map to some hardware units like function units, registers, interconnections and all, right. What will be our objective of corresponding to a function? That is something you should first understood, right. So, if say one function called 10 times in the main program, in the hardware what do we want? We need 10 copy of the function, because hardware is a fixed unit, right. So, it is basically there is a module which say so this function say doing some adder operation, multiplication operation, right. So, suppose there is a adder here and there is a mult here, and there are interconnections, right, it is coming like this. So, there is a marks here and so on. So, something like this, right. So, some function call, this is my function body say in the hardware, the hardware realization of the function body. Now, the question is that if I have 10 calls to this function, what will be our objective, right. So, our objective will be to create one copy of this hardware, right, in the hardware. If we create 10 copies of the hardware, that means my area requirement will be 10x, or resource requirement will be 10x, because if the x is the say 10 times, right. So, if the total requirement is say is 100 here, so 10 into 100. So, this 100 is some units. Okay. So, what I am trying to say is here, once I try to map these functions into hardware, my primary objective will be to create a one copy of the hardware, right, of corresponding to a function. But it might be that the way schedule has been generated, that sometime it may not be possible also, right. Because you schedule such a, there are two calls and there is no dependency of these two function, and probably schedule will do that they actually run these two in parallel, right. It can happen, because suppose it is taking argument a and b and this is taking argument x and y, there is no relation between these two. So, these two functions become independent to each other. In that case, that scheduler might schedule these two operations, this function in the same time step, right. So, you call these two function 1, so 2 instance in the same time step, this is a time step x. In that case, I cannot do that, right. But if the scheduler generate the schedule such a way that it is possible to have the non overlapping of their execution time, right. So, if that time where these functions multiple calls are actually getting executed, they are actually have non-overlapping, then I can create a one copy of the for the body of the function, and I can share that, or I can actually use that same thing to execute multiple calls, right. So, that will be my primary objective. The secondary objective will be is to, even if say I have a function and I understand that it is say that is only a function which is called only one times for simplicity, let us assume that. So, once I have one, so if I one function one call, then it definitely it will be a separate module, right. So, there is no question about that. My secondary objective will be, there is some multiplier, there is adder within the function call, and after this function call is done, this particular hardware will remain idle, right. So, it has no use further, because it is only one call, or even if say there are multiple call, after the call is completed, this particular multiplier or adder for this function body will remain idle for the rest of the time, right. So, my secondary objective will be, is it possible to share this multiplier or adder within the function body with the other operations, right. So, that will be my secondary objective. So, with this objective in mind, let us move on, right. So, let us try to understand that if there are function calls, how it look like, right. So, suppose the first thing is, if there are two calls of a function which is non-overlapping, right. So, suppose you have a function, say, so let me try to explain this. So, suppose you have a function here and there is a function here, and then so this function is scheduled, say, let me try to put it in properly. So, this function is scheduled this call, right. So, this is the function one call, and then say this is scheduled somewhere here. So, it is a 3 cycle, it needs 3 cycle to execute this. So, the same function it called 2 times, right. Since they are scheduled into different timestamp, if their execution time is non-overlapping, it is just like a normal thing, right. So, it might have say some multiplication operation followed by some add operation here. So, this multiplier is taking 2 cycle and this adder is taking cycle. So, I can definitely have a one copy of the module, right. So, if they are non-overlapping, the problem is easy. I can just take one copy of that, and then I can actually share the same thing with some other multipliers. Say suppose one addition operation is happening here. So, I can utilize one adder, right. So, one adder to execute this addition, this addition, this addition, because they are all non-overlapping, right. So, the summary of this discussion is, if we have multiple calls and their schedule time is non-overlapping, it is just like a flattened graph, flattened sequence graph, which is similar to a sequence graph corresponding to a basic block. And then this particular problem will remain a coordinate graph, this complete graph will remain this interval graph, because it is there is no problem, it is basically just it is same like having a sequence graph corresponding to a basic block. Okay. So, this is the case 1 where the function calls, the same function call multiple times and they are non-overlapping execution, multiple function calls multiple times and they are all execution things are non-overlapping. So, in summary, if all the function calls have their execution time in non-overlapping thing, I can flatten that sequence graph and I can get a single sequence graph where all these operations have this non-overlapping time, and hence I can solve the problem for normal sequence graph, non-hierarchical sequence graph, and this particular problem will become this the complete graph that we are going to get it from here, it will remain interval graph, and I can solve the problem using elliptic algorithm. Okay. So, this is the first part. The second part is that if say there are two calls and they are overlapping, right. So, this is the call say of function m, I call this is the function first time call, this is the function second time call, and they have some overlapping. So, the overlapping does not always indicate that there is no sharing possible, right. So, that is the first example I try to mean here. Suppose this function is doing one addition followed by multiplication, right. So, suppose it is doing a equal to b plus c and then say x equal to a star m. So, this is the function body, right. So, there is a addition followed by a multiplication, and the multiplication is 2 cycle operation. Okay. And say this function is executing times 1, 2 and 3, and this function is going to execute in time 3, 4 and 5, right. So, now you see here this is their corresponding intervals, right. You can see here that this multiplication intervals are overlapping, right, but the addition is not overlapping with this adder. So, I can So, although there are two calls, I cannot blindly say that since there is some overlapping of this function, I cannot do any sharing, that is not correct, but I can actually share a same adder to execute both these addition operations, but I need to separate multiplier, right. So, I need two copy of the multiplier and one adder. So, two multiplier and one adder to execute these two calls of the function, right. So, this is what I try to mean, that even if there are two function calls of a function which is have some overlapping, then it is not always the case that I cannot share anything. So, here I try to mean two functions. This is my function 1 where basically addition follows by multiplication, here multiplication follows by addition, right. So, this is function 1, right, this is function 1 and this is function 2 will be like this, that we can understand this, right, a equal to say b star c and then x equal to a plus say y, right, this is this function. But if it is the same function, then you can understand this will be plus followed by multiplier. So, then both can be shared, right. So, let me, so if I try to give the example, so suppose this is the function function 1 and then again I am calling the function 1 only, right. So, this is function 2. So, since it is basically it is the same operation, this is first addition followed by multiplication and then it is addition followed by multiplication. So, this is addition. So, what is going to happen here is addition followed by multiplication. Then you can see here this add is also non overlapping, mult is also non overlapping, right. So, mult is overlapping with add, but it does not matter because they are going to execute in different functionality, right. So, in this case I need one adder, one mult. So, I can actually have a one copy of the function here, right, one copy of the body, and I can actually do certain kind of sharing the multiplexing the input, so that I can actually execute both the addition operation for two calls using one adder and both the calls of the multiplier using one multiplier. And here the example of two different functions, this is function unit 1, this is function unit 2, and then it is addition followed by multiplication, here multiplication followed by addition, and here I can say that even if there are two different function, I can share the adder between these two function, but I need to do separate multiplier, right. This is what it talks about here. Okay. So, let me move on. So, suppose now I have multiple call to a same function, right. So, where they are overlapping. Okay. So, I discuss this scenario where there are multiple calls to the same function which is overlapping, but the operations I mean it can be shared, right. Now, suppose I have the multiple call to a function which is basically have a multiple calls, and in that case what I try to say that although there are some kind of resource sharing is possible, but creating only a separate copy sometime it is difficult, and in that case particularly this particular graph will not remain a interval graph. Okay. Let me explain what is that. So, let me take another example. So, suppose I have a function a, okay, which is addition followed by multiplication, right. So, you have say a equal to a plus b, then say x equal to a star y, right. This is the function body, and it is scheduled it called two times, the first call happening here and the second call happening here, and say in addition to that in the program there are some other multiplication operations are there, which is possible, right. So, say suppose so the call is like this. So, suppose your main code is look like this. So, main is like this, that you have a function which you are calling with a, b and y, and then suppose you are doing some independent operation, say m equal to n plus q, this is this operation, and then say this is n equal to m star x, right. So, which is say x, or say this is z, and this third operation is say w equal to u star v. Okay. So, this is, and then you have another call here function which is it is returning the function say d, and then I am calling the function with d say, and then I and j, right, some function. So, basically there is a dependency between these two functions because it is returning d and I am using the d here, and there is a dependency between these two operations which is reflecting this, and this is independent operation, right. I try to form this a corresponding example here. And now, if you have this, so the point here I try to make that if you have multiple calls, this problem won't remain as easily solvable problem, right. It is polynomial time, not polynomial time solvable problem. So, suppose you have this scenario and say this is the corresponding intervals, right. So, this is the first call, it is scheduled in say in this time step, and then this is when multiplied is 2 cycle and addition is 1 cycle. Okay. So, this is the interval corresponding to this operation which you can understand. And now, if you try to construct the complete graph, so there are 2 call to this function, there are 2 intervals, but in the complete graph I will have a single node corresponding to the function. Why? Because I want to create a single copy of the function, right. So, if I try to keep a multiple copy, there is no point of having function call, right. So, my objective is to make this function as a single copy. So, that is why I keep a one copy in the node in the complete graph. And now, there is overlapping from A to 2. So, there is edge here, 2 to 3 there is an edge here, 3 to 4 there is an edge here, and 4 to A, right. So, then this is my complete graph, but is this graph is chordal? Is this a chordal graph? Answer is no, right, because there is no chord. I have a cycle of 4 nodes, but there is no chord. So, this is not a chordal graph and hence this is not an interval graph, right. So, then if I try to solve this problem, I cannot apply Lefty's algorithm. Okay. So, the summary here is the discussion that even if 2 function calls have overlapping, I can share some of the resources. If there are 2 copy which is completely non-overlapping and there is nothing else, I can actually have a single copy definitely. And it is the point that if there are 2 functions which is have some overlapping, still I have some sharing possible for some certain kind of operations that I have already discussed. But in general, this problem when you have multiple call to a function and that there are some other operations, in that case the whole problem will not remain as polynomial time solvable, because the generated graph may not be a interval graph, because it will not satisfy the property of a chordal graph. Okay. So, this is the summary of the function calls. Let me move on to the next part, that if else. So, I already given an example that if else is a single node and it has branch like this. And then again I am going to say that this complete graph will not remain an interval graph. So, this will not hold even for if else, right. So, let me take an example, that suppose I have call like this, say suppose there are 2 multiplication operations, say let me write this main again, try to make this problem realistic. So, suppose I have a operation A which is basically say B star C and then B equal to A star X, right, this is the things, and then you have a if else, right. So, if some condition says let us say some C bar, you do this C equal to m plus m into n, else you do say f equal to m star say x, some arbitrary operation I am trying to make. Okay. So, if this is the code and that schedule might be like this, because I have a dependency from A to B. So, I will schedule them in different time step, but this if else does not depend on any of these 2 operations, right, because here all these operations are independent of these 2 operations. So, I can schedule it in parallel, right, I can schedule them in parallel to this operation. Suppose this is the schedule, it is generated by scheduler, and where if else it is the if branch and this is the else branch, and the if branch this C operation is scheduled here and D operation is scheduled here, because this is the else part, right. So, this is my else part operation. So, this is my schedule graph, and now let us try to put them in the interval. So, A interval is from 1 to 2, B interval is 2 to 3, S 3 to 4, and C and D is in 2 to 3, right, because these 2 operations schedule in 2 to 3. So, this is my intervals, because this is how I get the intervals for these operations. Now, let us try to draw the conflict graph. Okay. So, now you see A and C have a conflict. So, I have edge, I have C to D, I have conflict, I will come to that. So, now then C to B there is a conflict, and then A to D also there is a conflict, because they are actually having non-overlapping, right, A to D, and similarly B to D, right. Now, see here this C and D. So, let us consider this intervals and now try to construct the conflict graph. Okay. So, now you see here there is one node for each intervals, and A and C there is a overlap. So, there is an edge here, B and C there is overlap, there is an edge here, A and D there is overlap, so there is an edge here, B and D there is overlap, so there is an edge here. So, what about this edge? So, there is an overlap here, so we should have an edge here to make this graph, but this is not an conflict, because these two operations are mutually exclusive, right. When you have a if and else, I either will execute this operation C or I will execute the operation D. I am not going to execute both of them together, right. That means they are mutually exclusive. So, that means although their intervals are having overlaps, but the corresponding edge will not be there in the conflict graph, right. So, that means this interval does not reflect this conflict graph, right, and hence I am not able to map this node into an intervals such that whenever there are two intervals overlaps, then there is an edge here. So, that particular property does not hold, right. So, as a result, this complete graph which I obtained is not an interval graph, right, and if it is not an interval graph, I cannot solve the problem in polynomial time. So, I have to go for heuristic algorithm. Okay. So, the summary of this discussion is, for if else I cannot solve this problem in polynomial time or using left edge algorithm, I have to go for heuristic algorithm. Okay. So, now the last part is the loop. So, as we have discussed that loop, we have a loop body and which is something have another sequence graph. Because of the loop, the structure is little bit important to understand. Say this loop is executed in 3 cycles. Okay. So, this loop body have say 3 cycle operations, okay, and this is getting repeated. Okay. So, now you see here in the combined graph, whenever I am going to execute the whole thing in hardware. So, whatever the operation followed loops, right. So, these are the operation is this will has to wait till this loop is done, right. So, this loop has to execute separately and then everything has to wait, right, and similarly whatever the previous part is done, then only the loop will start, right. And then, so what I am trying to mean is that this loop body is have no overlap with the operations previous and the operation that is scheduled later, which was not the case for if else, because in the if else because they may be independent and they are actually having overlapping. So, I can put them here, right. So, the loop usually what we will do, we will put this as a separate entity and hence there is no overlap with this operation with this part and this part. So, I can take this whole thing together and I can actually solve the problem, and then in that case conflict graph will remain interval graph, and so we can solve the problem with loop. But remember, this is only for loop, and if I try to perform the loop independent of the other part. Okay. And since this is a repetitive part, I should not repeat with anything here or here, because I want to execute this part only once, this part say 10 times. So, I cannot just repeat any operation here with this or any operation here with this. So, then that particular operation will execute 10 times, because this part will be repeated 10 times or 20 times, right. So, that is why I can actually identify the resource sharing and then I am going to repeat this part 10 times. So, I can actually control this from the controller FSM. Okay. So, this is what about the loop. So, so we have already discussed the 3 construct, the conditional construct like if else, loops and function call, and we also discuss what is going to happen in the sequence graph in the resultant conflict graph if we consider all of them together. Okay. So, this part is done. So, I am going to conclude this particular class with a heuristic algorithm for clique partitioning problem. Okay. So, we have discussed that this problem, once it will remain, it is not a interval graph, then this graph coloring problem is become NP complete problem, and in the compatibility graph finding the clique cover is remain NP complete problem, right. So, in that case I could not have a efficient algorithm to solve the problem, but we should have some heuristic algorithm, right. So, I am going to discuss one such heuristic algorithm for the clique partitioning problem, which is applicable to the compatibility graph, right. This actually applies to the compatibility graph and a complement graph of this, where we use the graph coloring problem. But since the problem is dual, I can solve one of the problem, it solve both, right. So, what is the graph color, this clique partitioning problem? The problem is that you have given a compatibility graph, right. So, compatibility graph is what? It has set of nodes corresponding to each operations, and whenever there are operation which is actually is compatible, that means they are executed in different time step, there is an edge. So, if we have like this, that means say operation 1, 2, 3 and 4, then 3 and 2 and 1 and 2 is executing different time step, 2 and 3 is executing different time step, and 1 and 4 is also executing different time step, right. So, you can actually you can actually map this operation to some schedule. Let me try to put it here. So, 1 and 3 is happening here, say 1 and 3, 2 is happening here and 4 is happening here, right. But then I can have an edge from 1 to 2 and 1 to 4, 2 to 3 because 2 and 3 and 1 to 2, right. So, I understand this. So, this is what is the schedule. Okay. So, if this is the there, I try to find out the clique. So, I can actually find a clique of these two nodes because there are two nodes, they are interconnected to each other, and I can actually find this one and this one, right. So, I need basically if I go this way, I need basically three function units. So, these are all adders, right. So, I need 3 adders, but if I try to partition this way, say suppose I club these two together and this is the 2 clique, then I need 2 adders. So, you can understand that for the same problem different clique coverage give you different unique. So, the identifying the minimum. So, for this we need 2, right, because I need one to execute this part and say this part, right. Basically, there are 2 operations running in parallel. So, I need at least 2 such function unit. Okay. So, if we apply the heuristic based algorithm, then you may not always get this optimal one, you might get this one, but you get a solution, but most of the time the solution is good. Okay. So, let me explain this. So, I am going to this is my top level algorithm. So, I have given this complement graph and I find out a maximum clique, right. I found a clique from that and then I remove all the nodes part of this clique from the graph, and for the rest of the graph I am going to do the same thing until my graph become empty. Okay. So, this is what the overall this high top level algorithm, and let me understand this is the important problem, right, how to find out the max clique, right. So, the heuristic that I am going to use very simple one. What I am going to do it here is I will find a vertex which has the highest degree. So, I have a graph now which has the I find out the node which has the highest number of outgoing edge, right. I will select that node, say. Then what I am going to do, and so this is my C now. So, C now I have a single node. I will find out all the node which is adjacent to all the vertices in C. So, initially I have C only one node. Say among all the nodes that have connected to that, I will consider, suppose these are the node that are have a edge to C, right. If there is no such edge, I will return, right, I will return C, this is my maximum clique. And then what I am going to do, among all this node, I put all this node, this was a 1, 2 and 3 into the set U, right. I am going to put all the node into this U, okay. And then I am going to select a vertex from U and then I will make this, I will increase the C. Suppose I have selected this one, right. So, I have selected this one, then this now become my C, right, because this is a clique of 2 nodes, right. So, this is done, then I will go back again. Then I am going to find out all the nodes which has edges to adjacent to all the vertices, not only one vertices. So, now I am going to select this node, suppose it is also had an edge here, and say this node had also had the edge, so 1 and say 4. So, then I am going to select 1 and 4, not 3, because 3 has an edge to this node, but there is no edge to this node. Okay. So, next iteration I am going to select all such node which is adjacent to all the vertices of C. So, that means I can add any of them, right, because this will also form a clique of 3. Now, say I have selected 2, I mean say 4. Now, my graph this C become this, right. So, my C become this. So, it is a complete subgraph of 3 nodes. So, this is where I am going to grow the graph or the subgraph, complete subgraph, until I found there is no such edge, no such node which is connected to all the nodes, right. Then this is my maximum clique. So, this is what it will return, and then once I come back to this function. So, I got a clique, I will remove all the nodes of that subgraph from the graph and then I will call again, right. So, for the remaining graph I am going to do these things. Okay. So, let me take an example and explain. So, suppose this is my say comparative graph, right. So, what the algorithms are, find the largest node. So, what is the node with the largest degree is 4, right. So, I will select 4 and then I am going to identify all the nodes that had edge to 4, right. So, and you can find that the nodes 1, 6, 7, everybody is except 5, 2 and 3. So, they are all connected to 3, right. So, now I have to select say arbitrary one of them, say I have selected 7. So, my C become this, okay. Now, I have the 4 and 7, this is sorry, this is I have 4 and 7. So, this is my this is the C now, right. So, this is my C now, and I am going to find out all the node which is all connected to both 4 and 7. So, I have 1 which is both connected to 4 and 7. So, 1 will come here and 2 also connected to both 4 and 7, right. This is the only 2 node which is connected to both 4 and 7, not any other node. Okay. So, from there say I have selected arbitrarily 1. So, now my C become this, right. So, this is my C. So, now I have this 4, 7 and 1. So, this is the clique I have obtained now, and I try to find out U which is connected to all the nodes of this, and there is no such node which is connected to all 4, 7 and 1, right. So, there is no node. So, this will become 5. So, I will return. So, that means I found a clique with 3 nodes, right. So, this now I am going to remove this 1, 4 and 7 from the graph, because this is already removed. So, now I will remain the graph 6 this 6, 2, 1, 3 and 5. So, now I am going to take a node which is the highest degree, and which is maybe because 3 this node 3 also have degree 2, 2 has also degree 2, 6 also has a degree 2, and this node does not exist, and the corresponding edges also does not exist, right. So, okay. So, only node has the degree 2 is basically 3, because this edge does not exist, this edge does not exist, these are not there. So, after this my remaining graph will look like this 6, 2, 3 and 5, right. This is the remaining graph, because this part is already done. So, this is my remaining graph, and I can see only the node has a degree is 3. So, basically in the next iteration this will find a clique, and then this will be another clique, and this is another clique. So, I need basically I have 4 cliques. So, this is 1 clique, and this is 1 clique, and this is 1 clique, right. So, you can actually see that. So, I need basically 4 color, and this is the mapping. Now, here why this algorithm is not optimal, that I will explain. So, suppose here I selected. So, in the first iteration I found that 4 is the node, and there are all these nodes are basically adjacent to that, and I have selected 7, right. But if I select 3 in that time, so this will become my clique, right, because I cannot add more, right, and that way I am not getting the maximum clique of size 3, right. So, it may end up that in some cases you are having more number of cliques, right. So, probably you might end up having this is 1, say this is 1, this is 1 and this is 1, right. So, in I mean you might end up having like this. So, what I am trying to say is that since this is an heuristic algorithm, and this selection has no I mean there is nothing to decide that which vertex to select, is there any way you can minimize the size. So, this algorithm may not always give you the minimum number of cliques to cover the complete algorithm. Okay. So, but this is an efficient algorithm, because it runs in V plus E, and it can give you the clicks in quick time. Okay. But the solution may not be the optimal one. Okay. So, with this I conclude today's discussion. Thank you.